Okay guys, welcome back. We're going to get started on lesson 6-7, which will wrap up chapter 6. So that's good news. We can get started with our review, get this tested and out of the way so we can move on with the rest of the units. So there's not a ton. Again, it's kind of a short lesson. There's not a ton in here. Basically, we're taking what we learned in lesson 6-6, which was using the coordinate plane to describe geometric figures. And we're going to take that one step further and just learn how to write a proof using the information that we learn about a geometric shape in the coordinate plane. And they teach you, they go through one more theorem here, specifically about trapezoids, and how we can use that when building a proof using the coordinate plane. So the first thing, this theorem is about the trapezoid mid-segment. But I want to come down here first, and I just want to talk briefly about what exactly is a trapezoid mid-segment. So you've probably heard this at some point, but it's simply the segment that joins the midpoints of the non-parallel opposite sides of the trapezoid. So in this figure down here, our trapezoid mid-segment would be MN, because notice it goes from the midpoint of one non-parallel side to the midpoint of the other non-parallel side. So there's a few things that we can conclude about this. One, if M is truly a midpoint, and if N is truly a midpoint, we can see these marks in here. We break this into two equal parts. We break this into two equal parts. Right? We don't necessarily know that RM is congruent to AN, but we do know that RM is congruent to MT, right? Because that is the midpoint there. And AN is congruent to NP, that's the midpoint there. We also know that because this is a trapezoid, it has exactly one set of parallel sides. So obviously these were our non-parallel sides, so RA and TP are going to be our parallel sides. So we can look at these, and they have them marked as parallel as well. But we can also see that if we're going from midpoint here to midpoint here, that MN is going to be parallel to TP, and MN is also going to be parallel to RA. So it runs directly between those two. And we can also see that if we take TP and we take RA, we add them together. Notice there's no line above these. So they're referring to the length of TP and the length of RA. If we add those up and divide by 2 or multiply by 1/2, we get the length of MN. Which is just to say MN is the average of these two lengths. So we take this plus this, divide by 2, we're taking the average. Okay? So written a different way, and that's essentially what this theorem is referring to. I wanted you to be able to see it down here before we talk about it up here. The theorem, the trapezoid mid-segment theorem, essentially just says that the mid-segment is parallel to both of the bases, and that the length of the mid-segment is half the sum of the lengths of the bases. So just like we talked about here, the mid-segment MN is parallel to both RA and TP. That's part 1 of the theorem. Part 2 tells us that if we take the average of the two bases, TP and RA, their lengths, right, add them up, divide by 2, we get the length of MN. Okay, so now we take a look at how we can apply this theorem to an example. So if we look at the first example, we say, oh no, it's a trap, like Admiral Akbar from Return of the Jedi. But we have trapezoid TRAP, and they ask us to explain why we can assign the same y coordinate to points R and A. Well, it's a fairly straightforward explanation. We know that we've got one pair of parallel sides, and we can obviously see that RT and AP are non-parallel. So we can assume that TP and RA are, because they do tell us that it is a trapezoid. So we know that TP and RA must be parallel. Now, because TP is running along the x-axis here, right, we can see that they're one and the same. We can assume that RA must also be horizontal, right? The x-axis is horizontal, so RA also has to be horizontal. If RA is horizontal, we know that any 2 points on a horizontal line are going to have the same y coordinates. So R and A are both on a horizontal line, therefore they must have the same y coordinates. So, like I said, pretty straightforward for that one. We do have another example before we move on to the quick checks, though. This one's a little more involved. So first I wanted to take a second to explain how to get these points here. So they ask you to draw quadrilateral XYZW by connecting the midpoints of ABCD. So if we draw midpoint between C and D, between C and B, between A and B, between D and A, we get our 4 points. Now, if we didn't know these coordinates for the points, we could figure them out, right? If we take a look, we can see that this y value right here, right, this y value right here is 2b. Now, if this is 2b, and the y value here at A is 0, we know based on the definition of a midpoint that the midpoint is going to have a y value that's directly between 0 and 2b. So you can think of this as breaking this up into b, right? So from here to here would be 1b, and from here to here would be 2b. Same thing with 2a. If this is 2a out here, get a better marker. If this is 2a out here, and this is 0, then the x-coordinate of these two midpoints should lie between at A, right? From here to here is 1a, from here to here is 2a. You could plug into the midpoint formula and do the work that way if you're getting a little confused here. So instead of just looking at this graphically, we could go back to our midpoint formula where you take the two x values, so x1 and x2, and you take the average, right? Add them together, divide by 2. Same thing with y, right? y1 plus y2, and you divide the whole thing by 2. So you could plug into that formula as well to get all of these points if you wanted to do it the more manual way. So once we have these coordinates, now we can start looking at proving that this quadrilateral, right, XYZW, is in fact a rectangle. Moving on, we have to think about, well, what do we know about rectangles? And we know that in order to prove that a parallelogram is a rectangle, we can show that if the diagonals of that parallelogram are congruent, then we can say that it's a rectangle. So that's what we're going to attempt to do here, is to show that the diagonals are congruent. Well, to show that they're congruent, we need to find their distance, right, their length. So we're going to be using the distance formula, but we're going to be using the coordinates from our image up here. Okay, so you should have that in front of you. So to do that, we're going to find the lengths of the diagonals and then just show that they're equal, which will prove that they are congruent. So if we take the values starting with x and z, so again, if we look at here's x and here's z, right? If we're going to do a diagonal, we have to take opposite points. We've got negative ab and a negative b for our two coordinates. So we're going to plug that into our distance formula. We get negative a minus a squared, and then we get b minus a negative b squared. So we're going to get 2b, right? Because b minus a negative would be plus b. We're going to get minus 2a. So when we square those, we get positive, right? The negative 2 gets squared to positive 4, and a gets squared to a squared. We have to square both of those, the negative 2 and the a. Same thing here. 2 squared is 4, b squared is b squared. So we get this square root of 4a squared plus 4b squared. So now let's check the other diagonal. So we did x and z. Now we're going to look at y and w. And we have the values ab and the values negative a, negative b. So we'll come, plug those in here, and we can already kind of start to see the first part is exactly the same, right? Negative a minus a squared, just like it was up here. So we're on the right track. When we square this, or when we combine these terms, we get negative 2a. Combine these terms, we get negative 2b. And again, when we square them, the negatives disappear. And so we just get 4a squared plus 4b squared. Same as what we got up here. So we can see that these two lengths are the same, the diagonals. So the length of xz is equal to the length of yw. And because the diagonals are congruent, right, they both have the same length, we can conclude that the parallelogram is in fact a rectangle. Alright, so that just leaves us with the quick check. And the quick check looks kind of long, but really it's not too bad. Take it bit by bit, and especially since this was a shorter lesson, you should have a little more time to spend on the quick check. So go ahead. First it asks you find the coordinates of midpoints m and n. How do the multiples of 2 help? So again, think about if you're finding the midpoint between something with a 0 and something between 2, or something 2 of something, you're finding the middle of that. So you can talk about the multiples of 2 helping. Find and compare slopes, so that's not something that we've done thus far, but you should be able to do that. Finding the lengths was what we just did in the example. It says in parts B and C, how does placing a base along the x-axis help? So think about what we talked about, horizontal lines, and how that helps us with coordinates. And then it says use the diagram and explain why the proof using those points is easier than using these points. So maybe just do the first couple steps using these coordinates as A, B, C, and D, and take a look at how that might be a little more difficult. Alright, good luck.